Now that we have proved a very powerful theorem, that is the Riemann-Lebesgue theorem, we can get several consequences for free. I'm going to start listing them one by one. Most of the proofs are trivial. So what I will do is I will just indicate how to prove them and leave the details to you. So let me just list them as corollaries. Corollary 1. Let f from AB to R be a bounded function with only a finite set of discontinuities. Then f is Riemann integrable. This is because any finite set is of course a set of measure 0. So there's really nothing to prove. Corollary 2. So let AB be a closed interval, and CD be a subset of AB. Okay. Now we define chi CD. This is called the indicator or characteristic function of CD. This can be defined more generally for any subset, but I'm just defining it for closed intervals for the time being. This is by definition 1 if, so let me put of x, if x is an element of the closed interval CD and is 0 otherwise. So this is a function whose value is 1 precisely at the points of CD and 0 elsewhere. Okay. Then chi CD is Riemann integrable. Okay. Now the proof of this is just one line. Proof: the set of discontinuities of chi CD is a subset of these 2 points C, D. Just these 2 points are the only possible places where this function can be discontinuous. So it follows from the previous thing that says that any bounded function with only a finite set of discontinuities is automatically Riemann integrable. So I'm going to stop writing corollary and just write a numeral because it saves time. The product of 2 Riemann integrable functions is Riemann integrable. So let's see a proof of this. The proof is not hard. Okay, so of course I must write where these functions are defined. F from AB to R and G is also from AB to R. Okay. Now proof. So obviously F into G is bounded. Now the discontinuity set DFG, the set of points where the product FG is discontinuous, is of course going to be a subset of the set of discontinuities of F DF union the set of discontinuities of G. Note, I do not write equal to, I just write subset, think Y that this will just be a subset. Hence DFG is a set of measure 0 because DF and DG are sets of measure 0. Okay, this is a really short proof. Let's see the next corollary. The next corollary is somewhat involved. Let f from AB to CD be Riemann integrable. Be Riemann integrable. And phi from CD to R be continuous. Be continuous. Then phi composed with F is Riemann integrable. Is Riemann integrable. Again, the corollary looks a bit complicated, but the proof is very easy. Proof. Let df be the set of discontinuities. Set of discontinuities of f. Then the set of discontinuities of phi composed with f is a subset of df. Why is this true? Again, because the composition of two functions will be continuous at a point if f is continuous at that point and phi is continuous at f of that point. So if you take a point of continuity of f, then phi composed f will automatically be continuous at that point. Therefore, the only point of discontinuities of phi composed with f will be a subset of df. Again, think why I write subset and not equal to. Okay, and we are done. We are done because subsets of measure 0 set are measure 0 for the same reason as the previous are measure 0. Now, I had rambled on a bit about why I want to prove the somewhat technical Riemann-Lebesgue theorem, saying that many consequences will become fairly straightforward, and I have demonstrated at least a few of them. To make this demonstration even more potent, I want you to sit down on a nice afternoon and try to prove 3 and 4 directly from the condition that a function is Riemann integrable if and only if for each epsilon greater than 0 we can find a partition P such that UFP minus LFP is less than epsilon. Directly from that, can you solve problems 3 and 4? And you will realize that the techniques that you use to prove 3 and 4 put together with a little bit of tweak can be used to prove the Riemann-Lebesgue theorem itself. So why not just prove the Riemann-Lebesgue theorem and get it done for once and for all? Okay, so that's one observation that I wanted to make. Let's move on with the corollaries. Number 5. If f from AB to R is Riemann integrable, then so is mod f. This is obvious because the modulus is a continuous function and you can treat modulus of f as absolute value composed with the function f and apply the previous corollary. So it follows immediately. 6. Let A less than C less than B. Suppose f from AB to R is Riemann integrable. Okay. Then so is f restricted to AC and f restricted to CB, and integral of f A to B is just integral A to CF plus integral B to C to B f. Okay, again the proof of this is very easy. Proof. Okay, f restricted to AC and f restricted to CB are obviously Riemann integrable. Because the set of discontinuities of each function would be a subset, of the set of discontinuities of f. That is obvious. Okay, so both functions will obviously be Riemann integrable. Now observe that I can write f as f into chi AC plus f into chi CB. I can write the function f as a product of the function f and chi AC plus f into chi CB. Okay. Now, with a little bit of thought, it's now clear that integral a to b f is nothing but integral a to b f times chi AC plus integral a to b f into chi CB. This just follows from linearity, which we have established in an earlier module. This is just linearity. Okay. Now, the little bit of thought part comes now. This is nothing but integral a to b f restricted to AC plus integral a to b f restricted to CB. So this is the part that requires little bit of thought. When I say little bit, I really mean little bit of thought. Okay. Now the original proposition says it's integral a to c f plus integral c to b f. That is rather easy to see. Integral a to b f restricted to AC is actually same as integral a to c f restricted to AC plus integral c to b f restricted to CB. Why? Please check why this is true. Again, this also requires just a little bit of thought. Okay. So we have now seen several consequences of the Riemann-Lebesgue theorem. None of them are particularly difficult except the last one, which requires some thought, but they are all straightforward and easy consequences of the Riemann-Lebesgue theorem. I hope you come out of this module feeling that the effort that was involved in understanding the Riemann-Lebesgue theorem is certainly worth the hard work. Hope that you solve whatever bits that I have left for you. This is a course on real analysis and you have just watched the module on consequences of the Riemann-Lebesgue theorem.